This example shows you how to include friction considerations into our energy arguments. Alright, we have a car whose mass is 230 grams. It rolls across the floor with an initial kinetic energy of 0.46 joules. As it's rolling across the floor, friction works on the car. Friction does a total work of 0.30 joules. And the question is, what's the car's final speed? Now we know that friction slows the car down. How does it do that? Well, it works on the car. Any work that friction does on the car subtracts from the total energy of the car. So at any point, the total energy after friction has done its work is equal to the total energy before minus the work due to friction. Well, the car's rolling on a floor, so it has no potential energy. However, it does have kinetic energy. So, as it's rolling, its total energy is simply its kinetic energy. So the total energy before is simply 0.46 joules. The work that friction does is 0.30 joules. So the total energy afterwards is the difference between the two, or 0.16 joules. Now that we have the total energy after friction has done its work, we can calculate the speed. After all, the total energy is the kinetic energy because there's no potential here. And kinetic energy is 1/2 mv squared. So the kinetic energy, which is also the total energy, is 0.16 joules. The mass is 0.230 kilograms. We need to convert to kilograms to make the units work out. I assume you know how to do that by now. And we don't know the speed. When we solve for the speed, we find that it's the square root of 2 times 0.16 joules over 0.230 kilograms. I've shown you how the units work out in this equation, so I'm not going to show you that again. However, when you do the work, you find out that the speed is 1.2 meters per second. So after friction has done its work, the car moves with a speed of 1.2 meters per second.